Hi, Dr. Browne. Thank you so much for participating in our first interview. We have 8 questions for you today, both about your experience as a student and about your experience and work as a researcher. Before we get into the questions, to get to know you a bit better, could you introduce yourself?
Yeah, well, thank you guys for having me. I'm very excited. My name's Dr. Browne, and I am currently a researcher at the University of California, Santa Barbara. I am researching active matter, which is anything that can propel itself and move, much like living systems. And previously, I just graduated with my PhD from Princeton University, where I was studying polymer solutions, which are fluids that have been engineered with special properties for a variety of applications.
Now that we know a little more about you, we want to ask, how did you know in high school that you wanted to go into research? And how did you choose between pursuing academia rather than the science industry?
Yeah, that's a really great question. And actually, for me, I think I was perhaps a little atypical or a late bloomer. I actually didn't know I wanted to go into science in high school. I was good at science, and maybe that just made it kind of a little bit boring because it kind of just clicked and I didn't really see growth potential there. I was actually really into politics, oddly enough, and I thought I was going to go be a foreign diplomat somewhere.
Wow.
Yeah, but I mean, life is crazy and it pushes you in different directions. So I guess the moral I've always taken from that is not to be too surprised when things change, and also not to worry if you don't have everything figured out in high school, because I certainly didn't have this plan. One of the moments where things really clicked was during AP chemistry. I had a really good friend who was not really enjoying it very much. So he'd done a little study session. And as it turned out, I ended up kind of leading this study session and teaching them. And I mean, the topic was kind of just very like beginning of the course, but I really just enjoyed the teaching aspect of things. And I think that was one of the things I latched onto and why I eventually chose to go into the sciences. And now I'm going into teaching the sciences.
Wow. So like your experience in high school has kind of led up to what you like started to study in college and also where you want to go beyond that as well. That's really cool.
Yeah, very much. Yeah. And you don't have to have everything figured out in high school, because I certainly didn't.
Our second question is, looking back on college, what were some tips or advice that you want to give your former self? And what do you think is the biggest difference between being a graduate student in research as opposed to an undergraduate student in research?
Yeah, these are also really good questions. So I think undergraduate and when you're in college is very different than high school, of course, because the classes are much less structured. You have a lot more freedom in what you're going to study, what classes within that kind of major you're going to take. Even more than that, what you do with your time outside of that. So I think when I first arrived, I was at Purdue University for my undergraduate. I immediately tried to do like a million clubs, which I think is really the tendency in high school, to have like a lot of extracurriculars and just kind of really fill your time. And I burnt out doing that pretty quickly because the courses really are quite hard. They really demand a lot. And you need to kind of take a lot of, I think, more time just for doing things that you enjoy. And nobody's really kind of watching what you're doing in your spare time and evaluating it. So I think I learned eventually, but I wish I had learned earlier, to not worry about what everybody else is thinking, not worry about like trying to do what looks good, but to just focus on what I enjoy doing, what I enjoy learning, and what I want to do with my free time. And then that, I think, will naturally guide you into the right places. And that meant a balance of both school and academic things, extracurricular, but also athletic things, extracurricular. And so I think that was, the most important thing. One of the things that I ended up doing, my main extracurricular, was doing research in undergraduate, which is certainly not an extremely common thing. It's certainly very available as an undergraduate. There's a lot of laboratories, so you can join in and kind of work within them doing kind of small projects. So that's certainly not the norm, but it was really fun and I really enjoyed it a lot. So I actually worked in several different labs at Purdue, 3, because it took me some time to figure out what kind of research I liked as well. I started off doing some computational simulations that didn't really mesh with what I like to do. I was working in a chemistry lab for a while, which I thought I was really going to love, given my origins in AB Chem. But actually, I think didn't really mesh with me. And then I ended up working in a surface science lab that was studying explosives. And that really did, I think, match well, because I was working with some really cool equipment. It was a kind of very exciting type of microscope called an atomic force microscope that can image things at the resolution of an atom. And that really got me excited. And so I realized that I really like science where I can take cool pictures of things. And that ended up being what I kind of stuck with through the rest of my undergraduate. And then when I went to Princeton, I did the same thing. I found a lab with people I really liked working with, where I was able to take pretty pictures. And what a better job than to be allowed to take pretty pictures all day.
Do you think it's more common for people in science, their experience as an undergraduate to guide where they want to go as a graduate, or does that vary between different people?
Yeah, like it's certainly not the norm. A lot of scientists and engineers, when they finish their undergraduate degree, will go straight into industry and do science that actually goes into products that help people. And that's like, I think, a really exciting place that people go. And some people will go to graduate school. And among that crowd, it's a mix. So I took pictures in both, but the field I was in actually changed pretty dramatically. And so when I started graduate school, I had to kind of start all over and learn things from scratch, start at the bottom of the totem pole, so to speak. And I really enjoy that kind of like starting over and learning new things, but some people really kind of continue on in the field that they started in if they feel like they really mesh with it and they really like it a lot. But I think that's one of the nice things about research, is that people are very forgiving of you switching to a new field and learning things from scratch, because we're all, in this environment that's kind of centered around learning.
Well, speaking of college, our third question is, many high school students set goals for college, such as what high level degree they want to pursue. Mm-hmm. What's it like as a researcher after your student life and earning all your degrees? Did like anything change between like these two stages of your career?
Yeah, it's another really good question. So what I can maybe speak to most is life as a graduate student compared to a student, because graduate school, even though it's called school, is really more of a job or apprenticeship. And so it feels a lot different than school. So you leave undergraduate, there's maybe a couple courses, especially, maybe at the very beginning of the graduate program, but really it's usually something like 5 to 6 years of working in a lab, and you're kind of go off into the lab and you do your thing, and you have an advisor who's guiding you and helping you pick what things to do and making sure that you're kind of making progress towards deliverable projects that are having some kind of meaningful contribution to science. But it really feels like you're an employee, and you go into the lab and you do your work and you go home, and then you feel like, in many ways, like an adult. And so I think that's a really cool shift, and it gives you a lot of autonomy on what you're doing. And the goal, of course, is to do research that's really benefiting science as a whole. And so you're really doing work that is extending kind of beyond just learning. And I think a lot of what people feel through high school and college is that you're just kind of absorbing things from the outside. You're absorbing things that's already understood, and you just have to now understand it. And graduate school, I think, was the first time, even though I was doing some research during undergraduate, it was very guided by other graduate students. When I was in graduate school during my PhD, that was the first time that I felt like I was really kind of exploring the unknown and thinking about things that nobody else thought about. And, at the end, literally the only person in the world who's really thought this deeply about this topic, which is really exciting.
In like a laboratory setting, you have like different people who are at like different levels in terms of like academics, like undergraduate people who already have their degree, people who are working on their degree, the professor, whoever. So in that sort of like a hierarchical, I guess, like organization of different people in the lab, do you get like help from people who are just like a rank above you, and that kind of trickles down, or does the professor like actually supervise everything that's happening, or are they just like a guide person, and then you're like the rest of the team can kind of figure out what's happening and then report back later, like a month or something?
No, that's a really excellent question. And The answer is that all of those are correct. The best kind of question, because all answers are correct. It really varies a lot by lab to lab. And I mean, the reason is because an academic lab is really something like a small startup company and is run by one person, which is the professor or the principal investigator. And that principal investigator can kind of decide how they want to structure it themselves and find what works for them and what works for the people in their lab. And so when you're deciding what labs to join, if you decide to join a lab as undergraduate or go to graduate school and you pick an advisor, you really have a lot of freedom to kind of pick not only an advisor that you gel with, but the kind of laboratory structure and organization that you like. So I've been in labs that are very hierarchical, as you've said, where the PI, the principal investigator maybe talks to postdocs, and the postdocs have their PhDs and they're kind of in like an apprenticeship program before they, apply to become professors themselves. Then those postdocs talk to graduate students and have many graduate students working for them, and the graduate students have undergrads working for them, right? So then the undergraduates rarely speak to the principal investigator, which is one way to structure things, and that tends to work really well for very large labs. But my PhD lab, I was working with Sujidata at Princeton, and there it was very much not hierarchical. My advisor met with everybody individually, including like the postdocs, the graduate students, the undergraduates.
Wow.
And each person had their own project that was theirs. So instead of an undergraduate, doing a piece of a graduate student's project, oftentimes those undergraduates would have their own project, much like a PhD student's project. It would just kind of be maybe a smaller version of one of those projects. So that was more attainable to accomplish, during their time in the lab. But it varies a lot, and I see really a lot of merits of both.
So I'm guessing that the way that a lab is structured also kind of impacts how they divide up the workload and like areas of research between the different people.
Yeah, very much, yeah.
Our fourth question is, how did you find your interest in fluid dynamics, and how did you end up going into that area of research?
Yeah, so that's maybe also a funny story, because in my undergraduate, fluid mechanics was my worst course. It's the one I understood maybe the least, and it felt the kind of the most nebulous and scary. And it is traditionally, I think, a very hard field to understand. So it was at first a very scary field to go into, but I had met my advisor, Sujidata, and I just really, really meshed with him. And I feel like I really liked his style of communication, his style, like his philosophy about mentorship towards students. And that's something I really value a lot, is having an advisor who is there to guide you through things. And that's, I think, something I would encourage for everybody, in picking mentors during your undergraduate and picking an advisor during undergraduate if you go into research lab or going to graduate school, that you prioritize finding an advisor that you work well with personally, because it's a very important personal relationship. And he was studying fluid mechanics. And so at first it was scary, but I was actually encouraged that this is kind of the weak spot in my mind, the one part of my undergraduate that I don't think I understood well enough. And so that felt also kind of like at once the scariest, but also the perfect thing to spend 5 years really digging into. And now, of course, it's the thing I understand the most, which is, it's good to kind of take something that you didn't understand well and really kind of turn it into something that's your advantage.
Like a full character arc moment.
Full character arc, yeah.
So like fluid dynamics was still like the topic that you covered in your classes, say like during your time as an undergraduate, but you didn't particularly think you would go into it just because like you're interested in that topic from class or something. It was more about your interaction with your mentor, like guidance person as an undergraduate.
Yeah, that was how it was guided for me. A lot of people, again, it's a very personal decision. You're making very important life decisions. Some people do base it on coursework that they really liked a lot. And some people base it on their undergraduate research and whatever they were studying there, either because it was what they were already studying so they understand it, or because they really gelled with it nicely. They continue into that field. And I think I've really seen that succeed for a lot of different people. So there's not a right way to do it, as long, I think, as you're thoughtful about the field, and you're thoughtful about the people that you're going to be working with, because science isn't just you in a room doing science by yourself. Science really is a social job, and it really requires thinking through things that are very hard. And when you're thinking hard, it's good to be thinking with people that you enjoy thinking with.
Yeah, there was this quote by Hank Green on YouTube from a video that I watched like years ago, where he was like, so many people think science is like a one-person thing and we're like a bunch of nerds in like their own cubicles or something, but like science is like a team sport. And like he talked about that a little bit.
Yeah.
And I really want to find that quote again, but I don't remember what video it was because he made way too many videos on YouTube. So I'm kind of trying to like rewatch all of his videos that I probably watched before and find that quote, and it's taking a long time.
Let me know if you find it. I couldn't agree more. It really is a team sport. And I think a lot of really good science requires big teams and people thinking together. I couldn't agree more.
Our fifth question is, what did you study and look into while working on polymer solution flow in porous media? Would you say your research is a relatively niche topic, yet with broad applications?
Mm-hmm. Yeah, so I think that this is kind of the case with all areas of expertise, that on some level it's extremely broad. And as you kind of dig deeper into what was specifically done, it gets super, super narrow until at its like very deepest level, every publication should be unique and something that's a novel contribution to science. And especially kind of like that was like my PhD work. And so in many ways, I'm the only person in the world that kind of did that exactly. And so you can kind of look at it at the broad level, and then you can look at it at the very narrow level. And so at the broadest level, what I studied during my PhD is just anything that is soft. And what I mean by that, of course, you have an image like soft things are like squishy, but what I mean by that is things that are adaptable, that things that can self-heal or adapt to the world around them and perhaps make decisions on their own. And this is kind of maybe in contrast to what we call maybe like a hard matter, which is a lot of the science that was done in the 1900s, which is things like metals and alloys and transistors, things that are on off, things that are hard, they're either working or they're broken. And a lot of the kind of work in the field that I'm now in, which is called soft matter, is kind of redesigning those types of ideas with things that are more flexible, that can, in addition to physically bending, kind of more on a philosophical level, bend and adapt and have a softer response to things. To be a little bit more narrow, I'm looking at liquids that are soft. And by that, I mean that those liquids are responsive to certain stimuli. So if you'll excuse me being a little gross for a moment, a good thing to think about is the mucus in your body, right? Which, if you're sick or, just kind of during daily life, your body builds this mucus somehow, right? You can kind of feel it on your throat, you can feel it in your nose, and it's thick. And in many ways, it's almost a solid because it's just kind of lining your throat. It's not like dripping, hopefully, unless you're sick and it's dripping too much, right? Then something's going wrong. But what it needs to, it sneezes, it expels the mucus. And when you're sneezing, it's very runny. It flies right out of your nose. And then when it lands in the tissue, it's kind of solid-like again. And so that's a fluid that is kind of adjusting how thick it is, how solid-like or liquid-like it is to adapt to its environment, or to how quickly it's moving. And the way that your body does that is it has water, it's mostly water, and that your body is building long, flexible polymers, which are just kind of like repeated molecules called mucins. And those polymers are essentially stretching and rearranging, and they are retaining some kind of memory of the state that the fluid is in and allowing it to adapt. And so I study artificial versions of that, where we make kind of synthetic polymers and add them to water our cells to allow fluids to kind of be responsive and adapt to environments. And so the kind of work in my PhD, and I guess maybe you guys read some of it, even though it's very technical, is essentially trying to design fluids like that for like groundwater that will be drinking water that's sometimes dirty. And we're trying to develop techniques to kind of clean it out while it's still underground. So it's very hard to access, and you basically need to be able to put a fluid down there that can adapt to the environment and hope you kind of clean this out. And so the fluid that I've designed is one that the polymers themselves can kind of adapt to its environment.
That's very cool.
Mm-hmm.
Oh, so when you're like designing a new thing, like a polymer solution or a new kind of like robot technology or whatever, like depending on what your area of research
Mm-hmm.
is, when you're learning more about like earlier times in science, they talk a lot about this guy in this part of the world was researching this. Happens so that somebody else in a different part of the world was also
Mm-hmm.
researching it. And they were rivals and they hated each other. And they tried so hard to beat each other up by figuring this thing out first. But this one guy did, and the other guy was completely forgotten for the rest of history or something like that.
Yeah.
But like in more modern times, I feel like just in terms of what I know in like how science has developed, it seems like there's a lot more topics to explore just based on what we know so far and where we can go from here. So would you say as like we kind of progress into that time of like so many topics to explore kind of times, is it like less often that you find someone who is like also doing the exact same thing that you're trying to do in like another part of the world and you're like, hey, I'm doing that too, I'm gonna beat you? Or does that happen and you're like, hey, let's work together? Like, did that kind of dynamic change like compared to like back then?
Yeah, no, so there's a lot of really, I think, cool questions you had. So please make sure that I answer them all. It certainly does happen. I think that's maybe something in human nature, that there's some competition to discover something really exciting, especially with like really, really big discoveries, things that people win like Nobel Prizes off of. These kind of groundbreaking changes oftentimes have many people working on it and many people vying for the credit. But I think you're right that by and large, there's a lot more science today. And that's in part just due to a real explosion in science equipment and techniques. So the kind of microscopy that we have available, the different ways we can take images, the resolution, the ways that we have control over biology to be able to kind of do kind of very detailed tests, even just kind of like the speed of computers that allow us to analyze like much larger data sets than was possible even a decade ago, or to run more complicated simulations. All of these things mean that there's really a lot of open space to explore, and there's really not enough people to do it. So there's always kind of things you can find that nobody else is working on. And that's personally my philosophy, is there's no reason to compete with each other. Science, again, as we said, is a team sport. We're all working together to kind of expand human knowledge. So I don't really worry too much about getting credit for things or being the person who had made the big discovery. I just want to be doing something that I personally enjoy doing and that I know is a unique contribution. And there's plenty of, there's more than enough things to find for everybody to be working on their own thing and contributing. And I think when you're doing that, it's really good. I've always found when I find people, as you said, across the world who are doing similar things, we work together, right? We're not trying to compete with each other. We see that we're working on something similar. We each have a kind of a different angle that we're approaching these problems with, or we're kind of maybe looking at a slightly different application of a similar thing. And so we share that knowledge. And I think that that's a much more productive way to do science. I don't think everybody does that, but I think that is the growing norm, and I think really should be how people who are going into science view things, that you're sharing knowledge, you're kind of building one common base. And when you meet people like that, you should work together.
That's a very comprehensive answer on the question. Thank you so much.
Mm-hmm.
Oh, our sixth question is when you worked on your paper, elastic turbulence generates anomalous flow in resistance in porous media, you worked with one other colleague on the paper. Mm-hmm. So in terms of team size, what would you say is the difference in like communication, cooperation, mm-hmm. and how you split up the tasks between different people when you have a smaller team compared to like a larger team? of like a bunch of people with different expertise?
Yeah. On that one, that project was just me and my advisor, my PhD advisor, my professor. So that's maybe not the norm. Generally papers have many authors, something like 3 or 4, and some really big projects have 100 people on them, which is a little crazy to think about and how that kind of project is managed.
That makes me think, do they actually know all of like each other? Do they not know they exist?
Well, yes. I mean, for sometimes the projects really are these monumental, feats. Like a lot of the things that happen at like the gravitational wave detector at LIGO. I think many of like the kind of CRISPR papers have really massive teams because there's so many moving parts that no one person can really understand them all and make them all happen. And so it really is a team effort. And so it's important to kind of acknowledge that team effort and include everybody on this one thing. Because a paper at the end of the day isn't about the scientist. It isn't about showing off what you've done or what you've accomplished or what your ownership is. A paper is supposed to be, here is one thing that we've discovered. And that should be really just one conclusion. In an ideal world, you have some observation, and here's why we think we see that, right? And that I think is its most beautiful form. A paper is like that little story. You observe something cool, you explain it, maybe you have a model for it. And sometimes those observations it's good for that to be just kind of really thought deeply about by one person. So in the project where it's just me and my advisor, this was a really old problem. So this had kind of been a mystery for over 50 years. And it kind of was a problem that required looking at a lot of really old fields. So I had to kind of understand turbulence. I had to understand polymer solution rheology, which is essentially just how polymer solutions flow and respond to their environment. I had to understand a lot about geological science. I had to understand a lot about granular packings, which are 4 kind of very different science communities that have been around for a long time. And what that project really needed was one person, and I guess my advisor, to help guide me through some of the more tricky bits and make sure I was being very precise in all these pieces, to read it all and kind of see it as one big picture at once. And so that kind of a project, it was really good just to have the 2 of us working on it. But I've been on many other projects where, you need more people, where one person kind of really has an experiment locked down. One person has like a simulation kind of modeling that experiment locked down. And so one person's maybe working on a theory, which is the project I was on. I was like kind of like working on a theoretical model to explain the simulation and the experiment. And there again, it makes a lot of sense to have 3 different people working on it, and they're all kind of contributing something different. And I couldn't run the experiments, and the person running the experiments couldn't do the simulations, right? And so you're bringing your own thing to the table. And so again, I've never been on a team of 100 people on a paper, but I think it's a very similar thing where each person has their own skill set and they're kind of contributing one important piece that together has one kind of conclusion to science.
This is kind of like going off on a tangent, but if you have a project and you have an outline, like we need to do A, and then A will let us like know what we need to actually do for step 2, and then like we'll do the next thing, blah, blah, blah. And different people are going to work on those different steps, but person A needs to figure out this first before person B comes in and does the second step. Do they like need to communicate a lot with each other, or like do these people already know what they're supposed to do and you're just like, hey, just send me the data table or something?
Yeah, that's a wonderful question. I think that addresses something I maybe forgot to mention, which is that last author on all these papers, which is the principal investigator or the professor, is in many ways the project manager and handles a lot of those details. And so if you have a project where one person has to finish something and then hand it off, the job of the principal investigator is that they have this really good view of the field and what is the question that we want to answer, and what the tools we have available are to answer them. And they usually have a pretty good hypothesis for what we're going to observe, right? And so they are in a really good position to kind of direct all of those logistics and say, okay, you do this part first. When you figure this part out, let's all meet together in a room and chat, and then I'll tell this person now you can start the simulation, start thinking out this way. And there's usually a lot of back and forth in these things, but that's, every project requires a different type of organization, and usually it's the principal investigator who's the last author on that paper who really helps decide how to structure that organization.
So the principal investigator helps coordinate the whole process and also help how different people who are working on different aspects of the project to kind of work together and how they should be working.
Yeah, exactly.
Very cool. I hope that happens at like the high school level too, but it's not as coordinated.
Yeah. I mean, I think high school research is really tough, but it's very exciting. I think there's a lot of programs that are trying to make research or at least kind of like research projects more accessible to high schoolers, which is an exciting idea.
Our seventh question is, every research paper introduces either new information or a new connection of existing information. What were some breakthroughs in your PhD thesis paper, Elastic Turbulence Generates Anomalous Flow in Forest Media?
Yeah, so in that project, the breakthrough really was this very old problem that people had observed in the oil recovery industry, oddly enough. And there you have deep underground a rock, and that rock has little tiny holes in it, much like a sponge, except it's rigid, so the rock doesn't really move, but there's little tiny holes in it. And inside there's water, there's oil, there's a lot of kind of stuff underground, and you want to push out that oil. And you don't have a lot of control of what's going on. You're very blind. You can't see what's happening underground. And so they'd push things through these rocks. And what they found, kind of by trial and error, is that certain polymers, if they added a little bit to the water, would really help out a lot, which was mysterious. And part of the challenge with understanding what was going on and also controlling this process was that when they put the polymers in and pushed them through, the resistance to flow would jump up really quickly or really suddenly and unexpectedly, which is this anomalous increase in flow resistance. And there really wasn't any...
What's going on here?
What's going on here? Yeah, they really didn't know. And there was many hypotheses, but one of the really kind of hard things to kind of grapple with is that if you take the same polymer solution out and you just kind of put it in standard machines that measure the flow resistance, or we would call it the viscosity, but essentially it's how much resistance has to flow. The viscosity decreases. The faster you push the fluid, the viscosity or the resistance goes down, but in the rock it was going up. So it was completely opposite of what it should have been. So there was a lot of hypotheses about what might be going on, but all those hypotheses didn't really have any quantitative agreement. And so the breakthrough that we had was by building rocks out of glass, we finally had a way to look inside of them. So that required kind of a technique that my advisor had developed during his PhD many years ago to make these rocks out of glass. And then we use a kind of very special microscope that allows you to image inside this complicated space. And what we found very surprisingly was that the flow, even though everybody expected it to be very steady and smooth, much like kind of like a little creek, instead it was becoming very unstable and was fluctuating chaotically, kind of like a turbid river, like a whitewater rapids type deal. And so the flow looked completely different than what people were expecting. And the breakthrough we had was that this kind of chaotic flow was being generated because of the polymers in a mechanism that's only kind of recently been understood, and that those kind of chaotic fluctuations are creating this excess resistance, much like if you're trying to move upstream in a turbulent river, that's like much harder than through a smooth creek. And so that was the breakthrough, is that these polymers are creating this really kind of very different type of flow structure than what people thought before.
So the way you kind of approached the problem for this research paper was, let's take a problem which like people observed and kind of try to figure out the solution to, but have no idea how it works actually. And then let's scale it down kind of into this miniature heat-filled apparatus thingy, and then flow some solutions through it. and see what happens, because
Exactly.
like a part of the paper kind of talked about, we completely understand right now how this works at a 2D scale. But if we go to 3D, we have no idea. We're completely lost.
Yeah,
We don't know what's happening. I give up, you know?
exactly.
So
Exactly. Yeah. So this is
was
also
that
the
kind of the I
Mhm.
guess like step that you took from like going from 2D model of like this crazy flow thing to a 3D model with your bead apparatus?
Yeah, yeah, and I think this is really like a good lesson in one way that to do science, and this is the way that I often try to do science, is you have something really complicated that you observe in the real world, either in in rocks in the environment, right? And that's a very industrial application, or you observe something in biology, like how a cell is operating, or how a population is doing something, and the real system is quite hard to study. And so one technique is to try to build a simple version of it in the laboratory. And so I'm not taking the real rock. I'm kind of trying to build an artificial rock that's more simple, that is something that I can understand, I can control, I can image, I can model. And I can do all these things if I start really simple. And so the first thing you maybe do for a rock is, okay, you have a bunch of like kind of like weird grains that are packed together. Maybe the first thing I do is make it 2-dimensional so I can image it really clearly, because I just need a camera. I don't need any kind of weird microscope. And I'm just going to put like a little cylinder in there. And that cylinder is going to kind of be my model like grain, right? And so that's what people did, as early as like the 90s. And you can kind of watch how the fluid flows around this grain. And then you can say, okay, well, that was too simple. I need to add some of the complexity back into my system. So maybe I'll have multiple grains. And now maybe I'll have an array, a 2D-dimensional like grains all over, and maybe I'll like start adding disorder by shuffling them around. And as you add this complexity, you see, okay, I added this complexity. I can understand what's happening in this model system. Is this enough to understand the real world system yet? Or am I missing a really important piece of complexity? And so in this example, what we found is we've been adding in complexity slowly the field has been adding in complexity slowly for over 2 decades. And all of those added complexities give really important additional insights. But it turns out here that you still need that third dimension, that the 3-dimensionality plays a big role. And so you have to build an artificial system that has 3 dimensions. In other systems, I think it's a different story, but I think it's a similar philosophy of science, that you start really simple as possible, and add it in slowly. And this is a philosophy in physics that, so I'm in the physics department now at University of California. And one of the philosophies I've been told by several people is you understand something when there's not more things to add, but when there's nothing left to take away. And I think that's a really cool idea, that you understand something when you can duplicate it, but there's nothing, you can't take anything away. You have all the pieces that you need and nothing extra. And that's when you have all the pieces, like you understand what each piece is doing really well. And I think this is something that Feynman said, that what I cannot build, I do not understand. So this is, I think, maybe one of these philosophies in science that I try to do, is to build an artificial system that can recapitulate many of the exciting things that you see in a complicated system.
And this model has been being built up from like scratch by like a generation of scientists, like generations of scientists. And in your case, the person who kind of worked on a similar like this problem before like helped you on this project, and it kind of like went from one scientist to another. So like the whole scientific process or whatever isn't like one person going through this process and being like, okay, I'm done, and then like scrap that and like next person comes. It's like it continues over like different like a line of people, and they figure this question out in like 50 years.
I think a lot of science really is very long term, and this is why it's a team sport, because my paper, right, this maybe to me looks like it's the end of a long line of people that have done things and kind of written these papers that I've now kind of like seen, and it seems kind of like a message to me from the past. And in some cases, I've met the people who've written these papers, and they've given me tips and tricks on how to do these things, and what they're like, oh, if you do this, here's what I think is going to happen, and here's my hunch. Being guided by all of these kind of helpful direction from scientists that came before me. But in the same way that, what I just finished is just one more brick that other scientists are going to continue building on after me as well. And like, they'll be adding in more complexities, and then I think seeing even more exciting new insights that eventually will give us a more full picture of what's going on.
I think this is really cool. I'm just kind of sad they don't really like give this kind of a narration in like science textbooks. They're just like, there was this one guy and he figured this one thing out. Let's move on. I'm like, I'm sure there's more to it than that. Please tell me more. And they're like, don't have the time. Let's move on. And I get kind of sad about it.
Yeah, I mean, because it really, a lot of these things took, lots and lots of people, like thousands of people to contribute to them. And so there's, I think, maybe a human tendency, again, to assign ownership to one person. And that's just not really how science is done.
And it's kind of funny because like textbooks like give this one person who did this one thing, and then documentaries come and they're like, there was this hidden person who also worked on it. We have this crazy story, and then you're just like, they should have been on this story before, like you came up with this documentary. Like, this is sad.
Yeah.
It's kind of I guess like the disconnection between like how students learn science versus like what's actually going on in like the science field. And we just like have this image of like science is like people doing stuff like bam, bam, bam.
Room.
Yeah. Our last question number 8 is about these review papers. So some of your publications include review papers, but a lot of students don't really know the difference between a research paper and a review paper. They kind of look the same. They sound the same, honestly. So is like one of them better to cite for certain purposes, or they just have like different applications in terms of like online research? What would be your kind of advice to people who are like confused on like, we could be review paper, but I thought it was a research paper?
Yeah, this is another really great question. So the research paper, I think, is what we've been discussing this whole time, and that is a new experiment, some new data, a new simulation, some kind of new result. It's I think in its purest form, one new piece of science. Like, here's one new piece of delta knowledge that you're adding, and this is the first time that we've done this. Or this is a verification of a previous delta knowledge with a different technique that verifies that this was indeed correct. In contrast, a review paper is a summary of a whole field of these kind of delta knowledges, because each paper is, at the end of the day, trying to show you one new thing and then really be very rigorous and precise about proving that new thing, analyzing it in every possible way and understanding it well, and trying to justify their interpretation of the data and the way they're kind of framing that. It's hard to get a good larger perspective about what's happening across the world and over a couple years' time. And so review papers are essentially roadmaps for what everybody across the world is doing in a particular area of science. And so they typically summarize research articles over the past 5-10 years, sometimes 30 years, and try to give a perspective on everything that's understood currently. And so those roadmaps are, I think, really good place to start when you're new to a field. So I just started a new job here at University of California. I'm in a brand new field, so I'm starting over again. And so I'm reading review papers where it's some other person, probably much like me, maybe a professor who knows the field really well, who has summarized the current state of the field. And so they're kind of like, here's all the kind of papers that are really important, or that I think have really kind of guided the field and pushed it in new directions. Here's the summary of all of them. And here's what's left over. Here's what we don't understand. And I think that's the really crucial part and the exciting part of the review process is after seeing all of those things, all those papers in one place, that person who's writing it can see new connections between papers that weren't connected before, or to other fields that maybe the people in that field don't really talk to or don't really think about. And so oftentimes at the end of a review paper, there will be a little call to action where here are the big open questions that we need to understand, that we should start studying. And so when you're new to a field, that's often the first place to go, is to read these review papers, understand what's been done and what people want to be done. And then that's what you can work on, because there's a clear need.
So I'm kind of starting to go into this like small, I guess, research on like some bacteria and this protein that they make at school.
Mm-hmm.
And basically I've been trying to read a book, which is basically like a collection of review papers about this particular bacteria. And every one of the research papers, the chapters are basically like one research, like a collection of research papers that like somebody like compiled, which is I guess a review paper. And the formatting is basically like one thing we know, second thing we know, third thing we know, some more stuff we know. And then like in the last part, they would say something like, okay, so this is all the stuff we know. And this is probably how we should continue from here. Like, this is probably what we have left, but we don't know that. And I'm done talking about this now. Thanks for listening to my TED Talk. So
yes.
If I read those like papers that they were talking about and those discoveries like on my own, and they just gave me like a string of research papers, and they were like, synthesize this information into your own like summary and make your own, I guess, position about like where we should go next, I would honestly not really know what to say, and it's like too much to read. But I think as I've been reading these few review papers, I found it helpful because they would kind of like tell me and guide me, like nudge, nudge, wink, wink. Hey, this is probably what you should be paying attention to now that you're working on this protein and whatever. Also, watch out for this, because the last paper is about like taking care of your nematode, and it's kind of really cute. And they're like some cautionary tales about like don't do this, they'll die, or like don't do this, it's not good, stuff like that. So I guess it's kind of like them kind of leaving guidelines on like people who are then coming into the field, which I guess I really found helpful. And hopefully after that, I'll get to talk to some people who actually were working in the similar field and get some advice from them on like how to actually set up my project with some other person and work on it.
Yeah, exactly. I think at the end of the day, these literatures, as you're kind of realizing, are really large, and they're not only are they a lot of papers, which are, each of them takes a lot of time to kind of absorb and understand. So it's really kind of maybe unrealistic to understand all of those papers, and even in a review paper, but they're really kind of connected to all these fields around them. And so the more you dig, the more you're going to find. You're going to find that it's infinitely connected to everything else in science. So it's just too much, right? It's too much to kind of understand as one person. And this is why science, again, is a team sport, is you find your kind of area and you try to understand really well things that are close to that area, and understand a little bit things nearby, and then, at least be aware of things that are happening far away. But I think, as you said, you want to rely on these kind of review papers to help guide the way you think about these connections. And at the end of the day, talk to people, right? Science is a team sport. You want to talk to these people and get their perspective and hear their thoughts and say, here's what I'm thinking of doing. Here are my ideas. What do you think? And, a good scientist will share what they think and tell you what they're doing.
And they'll respond to a random high schooler.
Yeah, I mean, I think it's really good to try to talk to people for real, and you'll get a lot of insights just having these kind of conversations.
Thank you so much for all your really comprehensive answers and all your details on all of this. We really appreciate it.
All right. Thank you guys so much. This was a lot of fun.